Hello, my name is Morris Yao, and I'm here to talk about list decodable mean estimation in nearly linear time. This is joint work with Yeshwanth Cherapanamjeri and Sidhanth Mohanty at the University of California at Berkeley. We begin with estimating the mean of a distribution. Here, x1 to xn are d-dimensional vectors drawn IID from a distribution big D with mean mu and covariance bounded by the identity. Our goal is to output an estimate mu hat, which is close to the true mean in Euclidean distance. This can be achieved by taking the average of the samples, which is easy. Now, what if only an alpha fraction of our dataset is drawn from D, with the rest of the dataset x alpha n plus 1 to xn introduced adversarially? Henceforth, we refer to x1 to x alpha n as the inliers, and x alpha n plus 1 to xn as the outliers. Now, for alpha greater than a half, this is robust mean estimation, which in recent years has become a cornerstone of high-dimensional algorithmic robust statistics, in the sense that many robust statistics problems reduce to some form of robust mean estimation. But what if alpha is less than 1/2? Well, clearly, estimating the mean is impossible because the adversary could simply have introduced another covariance-bounded distribution some distance away with mean mu2. There is no way to tell whether mu1 or mu2 is the true mean. Nevertheless, this failure suggests a natural way to formulate this problem. Just as we list decode in the theory of error-correcting codes, perhaps it is possible to output a succinct list of estimators, one of which is close to the true mean. Formally, our revised goal is to output a list of estimators mu1 hat, mu2 hat, to mu hat big O of 1 over alpha, such that there exists an estimator in the list no more than O of 1 over root alpha distance away from mu. To declutter our notation for the rest of the talk, let k be equal to 1 over alpha. The problem of list decodable mean estimation was introduced by Charkar, Steinhardt, and Valiant, who provided a polynomial in NDK time algorithm for list decodable mean estimation with nearly optimal recovery, where optimal recovery is O of root k, and they achieved O tilde of root k. Since the work of Charkar, Steinhardt, and Valiant, we provide the first improvement to their runtime with optimal recovery guarantees. Our algorithm runs in O of nd poly k time, which is nearly linear when k is constant. Taking a step back, list decodable mean estimation is the simplest problem in a larger family of problems which fall under the umbrella of list decodable learning, which can be thought of as a generalization of classical robust statistics to the setting where outliers overwhelm the inliers. It is also a generalization of planted problems to the semi-random setting, such as semi-random planted clique or semi-random planted independent set. It also provides a simultaneous generalization of robustness and clustering. Indeed, the adversary could have introduced a mixture model or a robust clustering problem. Finally, it is also a model for semi-verified learning, where given an overwhelmingly corrupted dataset, the goal is to perform inference using a small amount of side information. Hence, in recent years, list decodable learning problems have seen a bit of attention. In particular, polynomial time list decodable learning has been established for regression and subspace recovery and mean estimation of structured distributions. For our problem of list decodable mean estimation of bounded covariance distributions, there has been concurrent work by Diakonikolas, Kane, and Kongsgaard running in n squared d k squared time, and a subsequent improvement to ndk plus poly k time by the same authors plus Li and Tian. First, we begin with an inefficient algorithm. We say a vector nu in Rd is a candidate mean if it is the mean of a subset of alpha n points with bounded covariance. Our inefficient algorithm is to enumerate all candidate means in Rd that are greater than omega root k apart in Euclidean distance. Clearly, the mean of the inliers mu is a candidate mean, and thus the inefficient algorithm outputs a list of candidate means, one of which is O of root k Euclidean distance from mu. Now, how do we make this efficient? A vast simplification of the list decodable mean estimation problem is to think of it as a clustering problem. The adversary introduces k-1 clusters of points with bounded covariance. The natural algorithm is to find a candidate mean and remove its associated cluster of points. We iterate this procedure on the dataset until all the points are removed. Here, we find the candidate mean mu hat 1 and remove the points in red. Then we iterate this procedure and find mu hat 2 and remove its associated cluster of points. And finally, we find mu hat 3 and remove the remaining points in the dataset. So how do we find a candidate mean? We try to answer whether a given vector nu is a good candidate. If yes, we output nu. Otherwise, we update nu with a new vector closer to a candidate mean. Pictorially, given a guess nu, we would like to answer two questions. Firstly, is nu a candidate mean? If not, find a direction to move nu so that it approaches mu, the true mean. Indeed, this is the approach taken in Cheng-Diakonokola's G for the robust mean estimation problem, where the direction to improve nu is the robust top eigenvector of the second moment matrix of the dataset evaluated with nu at the origin. Now, for the list decoding problem, how do we find a direction to improve our current estimate nu? Our main innovation is finding a direction to move that guarantees improvement. Our first key idea is to project onto a low-rank subspace. For intuition, consider the problem of clustering a mixture of k-bounded covariance distributions. Vempala and Wang prove that projecting onto the subspace containing the k-means shrinks the diameter of each cluster, but preserves the distances between clusters, enabling naive distance-based clustering algorithms to work. So here's an inspiration for an idea. Find an affine subspace containing the k-means robustly. Project and choose the best of a few random points. If we were working with an actual clustering problem, it stands to reason that one of the projected points is significantly closer to its associated cluster center than nu. So we update to the new point. Of course, this is an idealization of the list decoding problem where it is not true that the data is nicely clustered around k well-separated means. Nevertheless, one can apply the intuitions from robust clustering to find an affine subspace with the following win-win guarantee. We prove either one of the points is significantly closer to the true mean, one of the projected points is significantly closer to the true mean than nu, or there exists a dual procedure that removes a large number of outliers. With this guarantee in place, we can ensure progress. Either we update nu to one of the projected points, or we clean the dataset by removing far more outliers than inliers. This win-win enables our algorithm to converge to a candidate mean in no more than logarithmic iterations. Thus, the runtime bottleneck is that of finding the affine subspace. So how do we find the affine subspace? First, we define the chi-fan k norm of a matrix is defined to be the sum of its top k eigenvalues. Now let fk denote the set of matrices M satisfying its chi-fan k norm is less than equal to k. For example, F1 is the operator norm bounded matrices. We refer to Fk by its mathematical name, the fantope. We aim to solve for the min-max equilibria of the following convex-concave optimization. Let f of nu be defined to be equal to the max over m in the fantope and min over wi between 0 and bi. The sum from I equals 1 to n of wi of the Frobenius inner product of m with xi minus nu transpose, which is also equal to the equivalent min-max game because we are optimizing a convex-concave problem. Now, what is our interpretation of the min-max optimum? Our interpretation is either f of nu is approximately equal to the Euclidean distance between nu minus mu whole squared, or there exists a procedure for removing a large fraction of outliers. Now let m star be the maximizer of the max-min optimization. Then the robust affine subspace used in our algorithm is the top k eigenspace of m star, offset to nu. Now solving the min-max game can be reduced to solving the following pair of packing and covering SDPs. The packing SDP is a minimization over matrices M and W of the objective function trace of M plus trace of W subject to M inner product AI plus W inner product BI is greater than equal to 1 for AI and BI positive semi-definite matrices, where M is constrained to be positive semi-definite, W is constrained to be positive semi-definite, and the spectral norm of W is upper bounded by trace of W over K. The corresponding covering SDP is the maximization over Wi for summation I equals 1 to n Wi, subject to the sum over I equals 1 to n of Wi AI is PSD upper bounded by the identity, and summation I equals 1 to n of Wi Bi in K norm is less than equal to K, and Wi is positive. For those of us that are unfamiliar, a standard packing SDP finds the largest fractional number of ellipsoids that can be packed into a spectral norm ball. The only difference with our setting is that we are no longer packing into the spectral norm ball, but rather the chi-fan norm ball. Naturally, for k equals 1, this reduces to the standard packing covering SDPs found in much of the literature on fast SDP solvers. Now we talk about a multiplicative weights approach to solving an SDP. This was presented in a paper by Peng, Zhang, and Tangwan San. Now to analyze the performance of the solver, it suffices to analyze a two-player game where player 1 plays matrices M and W, and player 2 plays gain matrices based on stored weights Wi. After the end of the game, the solver outputs either a primal solution with trace of M plus trace of W less than equal to 1 plus epsilon, or a dual solution with summation I equals 1 to n Wi lower bounded by 1 minus epsilon. Here we elaborate on the two-player game. Player 1 plays matrices MT and WT at iteration t. Player 2 plays gain matrices FT and GT and updates a set of weights Wi. Player 1 gets reward MT-FT plus WT-GT, and so on and so forth until the game ends. At the end of the game, either player 1 outputs the average of the iterates M1 through M large T and W1 through W large T, and player 2 outputs a normalized version of W at the last iteration big T. Now, it is easy to apply standard regret bounds on the iterates MT and WT. What is difficult is computing the iterates, which are MT and WT, which are defined to be the argmax of F inner product M plus G inner product W minus M inner product log M, which is the von Neumann entropy of M, minus W inner product log W, the von Neumann entropy of W. Subject to trace of M plus trace of W is less than equal to 1, and the spectral norm of W is less than equal to trace of W over K, and M and W are both positive semi-definite. Now when K is equal to 1, the answer to the above optimization is simply M is equal to the exponential of F over the trace of the exponential of F plus the trace of the exponential of G, and W is defined accordingly. On the other hand, when k is greater than 1, it suffices to solve a simpler problem. We wish to find W star, which is equal to the argmax of W inner product some positive semi-definite matrix G minus W log W. Sorry, G doesn't have to be positive semi-definite. It just has to be bounded in operator norm. Subject to the operator norm of W is upper bounded by trace of W over K, and W is positive semi-definite. The exact solution has the following form. E is equal to the exponential of G, which is equal to its eigenvalue decomposition, summation I, lambda I, VI transpose, and let tau be a threshold, which is defined to be the max over all rho greater than 0, such that rho over the summation of I, minimum of lambda I and rho, is less than equal to 1 over k. Basically, we're trying to find a threshold that selects out the eigenvalues that are only a 1 over k fraction of the trace if all the eigenvalues above the size of rho are truncated. Then we define, well, we don't define, the argmax W star is going to be equal to the following closed form expression. It is equal to summation of I, minimum of lambda I and tau of VI transpose over summation over I, minimum of lambda I and tau. Essentially, we truncate the matrix exponential of G based on its eigendecomposition such that it is within the Chi-Fan norm ball. Unfortunately, for the sake of runtime, we only have approximate eigenvectors and eigenvalues. So what if we approximate a matrix M with M tilde, which is defined to be the projection of M onto its top k eigenspace, plus the projection onto the space orthogonal to its top k eigenspace. Sadly, standard PCA guarantees only provide that M minus M tilde in operator norm is upper bounded by epsilon. However, our analysis requires that M is greater than M tilde times 1 minus epsilon and smaller than M tilde times 1 plus epsilon in the PSD ordering. Our final contribution is a refined analysis of the power method. In conclusion, in our work, we developed the first near linear time algorithm for list learning in any regime. We developed fast solvers for packing and covering SDPs over fantopes. 3, we developed stronger guarantees for the power method. Some open questions. Are there fast algorithms for other list learning problems, such as list decodable regression or list decodable subspace recovery? Right now, all of these algorithms for regression and subspace recovery use the sum of squares semi-definite optimization hierarchy. And so, naturally, those algorithms are not very fast. So it is a very interesting question to see if you can get faster algorithms. Also, for list decodable mean estimation of structured distributions, it is a very interesting question to see if you can achieve bounds that are better than 1 over root alpha if you have, say, higher order hypercontractivity of the moments. So those algorithms are also rather slow because they use some very high degree polynomial methods. So faster algorithms would be very interesting. Secondly, is it possible to develop practical algorithms? So of course, if there are no fast algorithms, it's hard to have very practical algorithms. And this is definitely, there is very little known about this. I think the paper by Diakonikolas, Kane, and Klonsgaard, they provide a sort of spectral algorithm for list decodable mean estimation. And so it is conceivable that that is practical. It is interesting to see if there can be practical algorithms for any other list learning setting. And finally, the sort of very little is known about list decodable learning. So beyond subspace recovery and regression, some very natural questions is to ask about sparse statistical estimation, about list decoding and graph learning problems, generalized linear models. So there's a lot of open questions for polynomial time list decodable learning. In particular, in our paper, we show that for list decodable community detection, we can achieve the same results as a paper by Trevisan and McKenzie. And we think it is very interesting to see if there can be any extensions of that result as well. Thank you very much.